Good afternoon. We discussed rectangular coordinates and how to separate Laplace equation in rectangular coordinates. So we did del square phi is equal to 0 in rectangular coordinates, and that was in lecture 17. So lecture 17 was rectangular. And then in the Zoom meeting, we talked about cylindrical coordinates, how to separate variables in cylindrical coordinates. And if you have not yet looked at that, please do. I sent out a Zoom link, and also I have sent out lecture notes that I prepared for myself, so that you would have some notes handy to go with the video for cylindrical coordinates. In this lecture, we are going to discuss separation of variables for del square phi is equal to 0 in spherical polar coordinates. So in spherical coordinates, we have r, theta, and phi, and we're going to write the function phi of r, theta, and phi as r of r, theta of theta, and phi of phi. Like I mentioned earlier in the Zoom meeting, this is the coordinate phi, and this is the potential phi. So be careful there. And this is also phi. So you have three phi's in one equation, and they all look only a little different, and they mean something entirely different. This means the potential. This is a coordinate. This is a function, right? So bear that in mind there. And once again, when we are choosing a solution, we are not asserting that all the solutions are of the type r, theta, phi like this, that are separable into different components. What we are rather saying is that we are looking at this subset of solutions, and we are confident that we can find a unique solution to our problem, because uniqueness theorem assures us that as long as we apply proper boundary conditions, then we get our unique solution, right? So bear in mind that uniqueness theorem. If you've forgotten what uniqueness theorem is, I urge you to go back and revise it. So we're starting with this, and we would like to plug this into del square phi is equal to 0. And so I can write del square in spherical coordinates. We would have 1 over r square dou by dou r square dou phi by dou r, plus 1 over r square sine theta dou by dou theta sine theta dou phi by dou theta, plus 1 over r square sine theta square dou square phi by dou phi square is equal to 0. This is the Laplace equation in spherical polar coordinates. Now you see that r square is common all throughout, so I can just cancel it out, because the other side is just simply 0, and then I can multiply the entire equation by sine theta square. If I do that, what I would get is sine theta square dou by dou r square dou phi by dou r, plus here there is a sine theta in the denominator, so I would just get a sine theta in the numerator there, and I would get dou by dou theta sine theta dou phi by dou theta, plus here there is sine square theta, so it cancels out, and I get dou square phi by dou phi square is equal to 0. Then we want to look at solutions of the type r of r, theta of theta, and phi of phi. So I can go ahead and plug this in here. Notice that these are partial derivatives. These are partial. But when I plug this in, they would turn out to be full derivatives, because then this dou by dou r would only act on r of r part, because the rest other two, theta of theta or phi of phi, are independent of r. So dou by dou r would only act on r of r, so it becomes a full derivative. So then I can write this as theta of theta phi of phi sine square theta d by dr r square, sorry, this is the little r, dr by dr. Similarly, here I would have sine theta here the theta would only act on the theta of theta function. So I would have sine theta r of r phi of phi d by d theta sine theta d theta by d theta. Similarly, for the final one, we would have r of r theta of theta d square phi d phi square is equal to 0. Now I can divide this thing by the total function phi of r theta phi, which is r times theta times phi. So I'm dividing this equation here, this equation, let's call it star, by the total function phi. If I do that, what I would get is essentially, here the theta and phi would cancel out, so I would get s theta squared by r d by dr r square dr by dr plus here I would get here I would be getting theta sine theta divided by theta of theta d by d theta sine theta d theta by d theta, and here I would get 1 over phi d square phi by d phi squared is equal to 0. Now if you take a look at this equation, the last third term, this is only dependent on phi. The first two terms are dependent on both r and theta, whereas the third term is dependent only on phi. And when you add these terms, you get a 0. That means, just like the logic that we used while separating variables in rectangular coordinates or cylindrical coordinates, we can use the same logic here. This function is dependent only on phi, but this function is dependent on r and theta. So if they have to be constant. Otherwise, if this has r and theta dependence overall, after you evaluate this, then it can in no way cancel out with this phi part. They can only cancel out if each of these terms is equal to a constant, and so we're going to call that constant minus m square, and here plus m square. So m square minus m square will give you 0. So we're equating each of these r theta part, the first two terms, to plus m square, and the last part minus m square. Right, that's the first step of separation of variables. So I'm going to write the equation for the third part. So if I write that, I would get 1 over phi of phi d square phi of phi by d phi square is equal to minus m square. Now you can clearly see that for this, phi of phi is equal to e to the power plus or minus im phi, our solution. If you look at this equation, this could be written then as phi of phi d phi square is equal to minus m square phi of phi. Right, so if phi of phi is e to the power plus or minus im phi, then I would have d phi by d phi would be equal to plus or minus im e to the power plus or minus im phi, and a double derivative would be plus im, again the same factor, and then you have plus im phi, and here you have plus minus and plus minus, so irrespective of whether it is minus or plus, you get an overall plus because you're multiplying it twice, the same thing. And then I have I and I, so that is I square is minus 1, and then I have m here, so m square e to the power plus minus im phi, or that is equal to minus m square e to the power plus im phi. This is the function. So we have obtained d square phi by d phi square is equal to minus m square phi of phi. So now we know the solutions for the phi part, but we also know our condition if my system is such that if I have, let's say, a spherical conductor, okay, let's say if I have a spherical conductor, and and my system is such that phi goes from 0 to 2 pi, right? If phi goes from 0 to 2 pi, then we must have phi of phi should be equal to pi of phi plus 2 pi, right? So this need not be the case for all the problems. There may be some problems where you may have a certain configuration of the conductor where you don't have 0 to 2 pi, where you go from, let's say you have a wedge. Let's say you have a wedge in the conductor and the angle is only a beta, then you may have different constraints there on theta or phi depending on the problem. But in general, if phi goes from 0, then that means e to the power plus or minus Im phi should equal e to the power plus or minus Im phi plus 2 pi, or that is plus or minus Im phi e to the power plus or minus Im 2 pi. And this factor would be 1 only if m is an integer. Right? So that's one of the conditions for periodicity, that m has to be an integer. So we looked at the third part of the equation. We just looked at this part, this third part of the equation. How about the part concerning r and theta? So what I'm going to do is I'm going to write the equation for r and theta separately now, so we can see how that looks like. So if I write the equation separately for r and theta, I would have sine squared theta r by dr, r squared dr by dr, plus sine theta, theta of theta, d by d theta, sine theta, d theta by d theta is equal to m squared. Now if I divide this entire equation divided by sine squared theta, then I would get 1 over r d by dr, r square dr by dr, plus 1 over theta sine theta d over d theta sine theta d theta by d theta. If I bring this m square to the other side, I would have minus m square by sine square theta is equal to 0. Now if I look at this equation, I have the first term which is dependent only on r, and these two terms are dependent only on theta. So now I can use the same logic like how we have done before, that each of these parts, which is dependent only on r and dependent only on theta, must each equal a constant, just like how we got this m square in the first place. In a similar way, these two parts, the r part and the theta part, also have to equal a new constant. And here we're going to do a little bit of a trick, and that is we're going to equate this instead of calling it previously we called it k square or nu square, or here m square. Here we're going to do it a little bit differently, and we're going to call this constant L into L plus 1. The reason we do this is when we express this constant as L into L plus 1, we have a very nice way of solving the differential equation, and that's why we are including it here. So that would be the r part, and the theta part would be 1 over theta sine theta d by d theta sine theta d theta by d theta minus m square by sine theta square. That would be equal to negative of L into L plus 1. So when you add these two parts, that is part 1 and part 2, when you add these two parts, you get 0, because each of those equals the same constant with a change in sign. So we already got the solutions for phi. The solutions for phi are e to the power plus minus Im phi. And now we have two more equations, one equation for r and another equation for theta. So in a similar fashion to the equation for phi, we're going to figure out what is the solution r of r in general, and then we're going to figure out what is theta of theta, and then we'll put all these together and get a general solution. So the goal here is to use separation of variables to get a general solution, and based on the specific problem, we can apply those particular boundary conditions and get a unique solution from this generalized solution. So right now what we're trying to do is we're just trying to figure out what the solutions are generally. We're solving del square phi is equal to 0. We have not put in any specific boundary conditions. We have not imposed any specific conditions on the problem. The only thing that we did is we are looking at one subset of the solutions to Laplace equations. That subset is where we can express phi as r of r, theta of theta, phi of phi. This is all we are trying to do. And we figured out how phi of phi should look like, and now we're going to figure out how r of r is going to look like. So let me rewrite this r equation. So r equation would look like 1 over r of r, d by dr, r square dr by dr is equal to L into L plus 1. Now for this, the general solution is r of r is equal to some a times r to the power L plus some bl times r to the power minus L plus 1. So we can check that out very simply, and the way we are getting this is by guessing the solutions, right? And the way we guessed it is from this constant, just like in the previous case, we had a nu to the power r nu and b nu times r to the power minus nu in case of cylindrical polar coordinates. In a similar fashion, we are guessing this solution and see if it fits this equation. So if I do dr over dr, I get L times AL. This AL and BL are constants which would be determined from boundary conditions specific to the problem, right? So then I have R L minus 1 plus BL minus L plus 1 R minus L minus 2, right? And then if I do R square dr by dr, I would get L AL r to the power L minus 1 plus 2 would give me L plus 1 plus BL, I have minus of L plus 1 times r to the power minus L, right? So now if I do d by dr of r squared dr of dr, we're just trying to see if this solution fits this equation, and that's what I'm trying to do. So if I do that, I get L into L plus 1 AL r to the power L plus BL minus of L plus 1. Now again I get another minus L, and r to the power minus L minus 1, so that's minus of L plus 1, and so I have L into L plus 1 AL r to the power L plus, there is one minus sign, another minus sign, so overall they become plus, and I have BL times L into L plus 1 r to the power minus L plus 1. So if I pull out L into L plus 1 as a common factor, I get AL RL r to the power minus L plus 1, and that's what we started with. So this is equal to L of L plus 1 into R of R. So this is indeed a solution to this equation, right? So we figured out two parts now. We started with phi of r theta phi is equal to r of r, theta of theta, and phi of phi. We figured out this is e to the power plus or minus Im phi, right? And we figured out that this is something like AL times r to the power L plus BL minus L plus 1, right? And here we saw that this m must be an integer, and here we have not yet said anything about L because we have not yet looked at the theta part, which is the third and the last missing part. So now I can rewrite the equation for theta as well. That is, I would be going back to this equation, right? That's the third part that's left. So if I rewrite this equation, that's the theta equation here, I'm going to rewrite that here. So we have 1 over theta sine theta d by d theta sine theta d theta by d theta minus m square by sine theta square is equal to minus L into L plus 1. Here we have a minus sign. Recall that we equated the R part to plus L times L plus 1 and the theta part to the negative of that, so that they could cancel out in the original equation. So now here, to simplify this equation, we'll suppose that x is equal to cosine theta. Right? We're doing a change of variable, so we're going to simplify this equation. So we're going to call x as cosine theta. Then you have dx would be minus sine theta d theta. Right? Or you can write d theta minus dx by sine theta. Right? So now let's look at this. We have d by d theta. So d theta of theta by d theta. So then I can write this as d theta of theta. But instead of theta, I'm going to make it x, because I'm calling x as cosine theta times dx, and then dx by d theta. So from here, dx by d theta would be equal to minus sine theta. Right? So that would be equal to minus sine theta d theta by dx. This x is not a spatial coordinate x, y, z. We're just calling it x as a variable, and we're equating it to cosine theta in this case, right? So then I get d theta of d theta as minus sine theta d by dx, or I can write d by d theta in general as minus sine theta d by dx. So I'm going to plug this into the equation. So I would have 1 over theta sine theta. This d by d theta is minus sine theta d by dx, and then I have sine theta here, and this d by d theta will give me another sine theta d theta by dx, right, minus m square by sine theta square is equal to minus L into L plus 1. So we have supposed that x is equal to cosine theta. So if x is equal to cosine theta, then 1 minus cosine theta square is sine theta square, or 1 minus x square is sine theta square. Right? So here I have sine theta and sine theta cancel out, and I have a minus sign here and a minus sign here. So they both multiply, and I get plus sign. And here I have sine theta times sine theta, so I can cancel this and just write as sine theta square. Right? So I can rewrite this as 1 over theta d by dx. Sine theta square is 1 minus x square. Right? That is what it is here. Times d theta by dx minus m square by 1 minus x square is equal to minus L into L plus 1. I'm going to rewrite this on the next slide. All that we did was a change of variable by calling x is equal to cosine theta. We converted an equation that looks like an equation in theta to an equation in x. This x is not the spatial coordinate. We're just calling it as a temporary variable here, x is equal to cosine theta. So I'm going to write this on the next slide again. So that would look like 1 over theta, right? 1 over theta sine theta. Oh, sorry. We have removed all the thetas. 1 over theta d by dx of 1 minus x square d theta by dx minus m square by 1 minus x square is equal to minus L into L plus 1. Now if I multiply all throughout by theta of theta, multiply by theta of theta. Then I would have d by dx of 1 minus x squared d theta by dx minus m squared theta by 1 minus x squared plus L into L plus 1 times theta of theta is equal to 0. Right? So this, in general, gives us solutions called Legendre polynomials. This is a special equation. We will not have time to go into the mathematical details of Legendre polynomials in this course, but if you have taken any course in mathematical physics, or you can refer to the suggested prescribed book Afkin and Weber if you want to learn more about this Legendre polynomials. But Legendre polynomials are solutions to these equations, and we can divide them into two types. One for m is equal to 0. So if m is equal to 0, this equation would look like d by dx 1 minus x squared d theta by dx plus L into L plus 1 theta of theta is equal to 0. So in this case, the Legendre polynomial for m is equal to 0 is represented as p. Legendre polynomials are symbolized with p, and that would be equal to 1 over 2 to the power L factorial d by dx to the power L x squared minus 1 to the power L. So these are the Legendre polynomials for m is equal to 0. And recall that x is equal to cosine theta. Right? We substituted x is equal to cosine theta, and that's what this x means. This x, again, is not the spatial coordinate. Right? So we can see simple properties of these Legendre polynomials. So we started with phi of r theta phi, and we suppose that this was equal to r of r, theta of theta, and phi of phi. And we figured out that for this the two solutions are plus or minus Im phi. For this the solutions are AL RL plus BL minus of RL plus 1. And for this we have seen, especially for m is equal to 0 case, we have Legendre polynomials PL of x, which look like 1 over 2n L factorial d by dx to the power L x squared minus 1 to the power L. So here also we have two solutions, but for theta we're looking at only one solution, only for 1L, and we don't have a second solution. We expect two solutions because the equation that we started with, it was a second order differential equation. We had d by dx and d by dx. The initial equation we started with was a second order differential equation, right? But here for this thing we don't have the other solutions, because the other solutions diverge or go to infinity, and they become physically unacceptable. The only physically acceptable solutions for the theta equation are this, and to see why they are the only physically acceptable solutions, we'll have to go deeper into what Legendre polynomials actually mean, and which is beyond the scope of this course. So you can look up any mathematical physics textbook like Afkin and Weber to learn more about Legendre polynomials. So another interesting property of Legendre polynomials is that they are this PL of x is equal to PL of minus x if L is even, and PL of minus x is equal to minus PL of minus x if L is odd. So depending upon the nature of even or odd function, whether L is even or odd, we have PL, the polynomial itself, to be even or odd. So we can take this formula and generate some of the functions. So if L is equal to, let's say, 0, if L is equal to 0, you can clearly see that PL is equal to 0 of x is simply 1. And if L is equal to 1, I would have P1 of x. That would be 1 by 2 to the power 1 factorial, d by dx to the power 1 times x squared minus 1. So that would be equal to 1 over 2. D by dx of x squared minus 1 would give me 2x. So this 2 and 2 cancel out, and I would get x. So P1 of x is x. Similarly, we can also write so we got P1 of x, we got P0 of x to be 1. So the subscript that I'm writing here, that's the value of L. So in general, we have PL of x as 1 over 2 to the power L, L factorial, d by dx to the power L, x squared minus 1 to the power L. So P0 of x was 1, and P1 of x is equal to x, like we have just seen. What would be P2 of x? P2 of x would be 1 over 2 squared, 2 factorial, d by dx times d by dx of x squared minus 1 whole square. Right? So that would be equal to 1 over 2 squared is 4, 2 factorial is 2, so 1 over 8. Right? And then we have d by dx of this, so I would have 2 times x squared minus 1 times 2x, right? So I have 4 here, so that cancels out, and I get 2 here, so that would be equal to 1 over 2 d by dx of x into x squared minus 1, right? So that would be half. That would give me x squared minus 1, the first term, plus the second term is x times 2x squared. Sorry, x times 2x. So that would give me half x squared minus 1 plus 2x squared. So 2x squared plus x squared is 3x squared, so I get 3x squared minus 1. So P2 of x is something like half 3x squared minus 1. And you could do the same thing for 3, and you would get P3 of x is equal to half 5x cubed minus 3x. So you can keep doing this. So these polynomials are the solution to the equation here for theta. And the special property is these functions are even if L is even, and they're odd if L is odd. Let's see if that's true here. So 0, so that's 1, right? So that doesn't matter. So 1 is odd, so L is odd for when L is equal to 1, L is odd. So L is odd here because L is equal to 1. So we can see P1 of x is equal to minus of P1 minus x. P1 minus x would be minus x, so minus of minus would give me plus, right? Look at P2 of x, right? P2 of minus x would be half times 3 times minus x squared minus 1. It doesn't matter because you're squaring it, so I get half 3x squared minus 1, which is identical as P2 of x. So when L is 2, we see that the polynomial is even, that is minus. So when f of minus x is equal to f of x, we call that as an even function. And when f of minus x is minus f of x, we call that as an odd function. Right? So we see that when L is even, we have an even function, and when L is odd, we have an odd function. Right? So this is very nice because then we can look at some integral that looks like this between minus 1 and 1, right? And we can look at dx PL of x and PM of x, or let me rewrite it as PL prime because we already used M for the phi equation. So just two different L's if I do that. And here we have taken the limits as minus 1 to 1 because again we supposed x is equal to cosine theta, and cosine theta goes from minus 1 to plus 1. Those are the limits. And so if we look at this integral, right, if L is not equal to L prime, right? If L is not equal to L prime, then what we get is we get this integral to be 0. No matter what L and L prime are, we get that to be overall 0. This is a special property of Legendre polynomials. And when L is equal to L prime, the answer is 2 by 2L plus 1. Right? Or we can write this as minus 1 to 1 at the dx PL of x and PL prime of x as 2 by 2L plus 1 delta LL prime, where this delta LL prime is the Kronecker delta. So this relationship, when L is not equal to L prime, the integral being equal to 0, this is called orthogonality. That means these two things are mutually independent of each other. And one quick way to see that is, we know that, for example, if I take L is equal to 1 and L prime is equal to 2, just a simple example. This doesn't cover all the types, all the different combinations, but if you just pick one combination that looks like this, that for L I pick 1 and L prime I pick 2, then I would have minus 1 to 1 dx PL of x, or P1 of x and P2 of x. We know that when L is odd, PL of x is odd, right? And when L is even, PL of x is even. That's what we have seen on the last slide, right? And so this is an odd function, and this is an even function. So overall, you get odd times an even function gives you an odd function. So if you have an odd function, that means overall odd function f of x is equal to minus f of x. So if I were to plot this PL, P1 of x times P2 of x, the product, which is an odd function because P1 of x is odd, so it's like saying negative times positive gives you negative, right? So odd times even function gives you odd. So f of x is equal to minus f of x. That's the definition of an odd function. So if you just look at this product, for example, if the right side is like this for x greater than 0, then for x less than 0 it would exactly be opposite, but in the opposite direction. So this would be between minus 1 and plus 1. That's the nature of an odd function, that f of x is x. For x less than 0, negative, you would have this. So when you integrate from minus 1 to plus, this gives you negative area, this gives you positive area. Overall area would be 0. And that's what we get in an integral. We get the area under the curve. So if you have an even and an odd function, you get the overall area to be 0. And once again, bear in mind that here x is equal to cosine theta, x is not a spatial coordinates. So when functions like this, like Legendre polynomials, they satisfy this orthogonality condition, and we have this between minus 1 and 1. We call them as complete functions, and in general we can combine the solutions for phi coordinate. The solutions for phi coordinate were e to the power plus or minus im phi, and the solutions for theta coordinate are PL m of x, and remember that x is cosine theta, and these are Legendre polynomials. We can combine this theta and phi, both the angular parts, into one thing called spherical harmonics. Spherical harmonics are defined as y lm of theta phi. This is the symbol for spherical harmonics, and they essentially are expressed as square root of 2l plus 1 by 4 pi L minus m factorial by L plus M factorial PL of M cosine theta times e to the power I m phi. So this factor that we are putting, this is called a normalization factor. We're just adding this extra factor. This is just a constant, so that when we integrate, when we perform an integration over both theta and phi, right, over both d theta and d phi, we do the integration, right? We have a sine theta here because that's the scale factor for theta for integrating in spherical coordinates. When we integrate something like y L prime M prime, the complex conjugate, because we have a complex number here, times y L M without complex conjugate when we do this integral. And obviously for theta we are going from 0 to pi, and for phi we are going from 0 to 2 pi. We want this to yield 1 if L is equal to L prime and M is equal to M prime, and 0 if L is not equal to L prime and M is not equal to M prime. So to get this 1 or 0, we are adding this extra factor, right? Because previously, if you recall, this when I do the integral of the Legendre polynomials, I get 2 by 2L plus 1. I don't get 1. So I'm taking a square root of this and multiplying it. So when I multiply these two terms, I get something like that 2L plus 1 term, which makes the integral look like 1 instead of 0, instead of some number, right? So we call this as orthogonality. So we say that spherical harmonics are orthogonal, that is, they are mutually independent of each other. Or in other words, we can represent any function as a sum of spherical harmonics. So we can take these spherical harmonics and write any function in theta phi as a sum of these spherical harmonics. So we'll stop here with spherical coordinates and just quickly recall what we have done. We started with del square phi is equal to 0, and in general, in spherical polar coordinates, we looked at some specific solutions that look like r of r, theta of theta, and phi of phi. And as I mentioned, this is just a general solution, and we get the particular solution by applying boundary conditions. And by separating the variables, we have seen the solution to this looks like BL r to the power minus L plus 1, and the solutions to these two are y LM theta phi, right? So y LM theta phi combines the Legendre polynomials, right, of cosine theta and e to the power I m phi, right? So it combines Legendre polynomials and the other solution. So we together, putting them together, we call them the spherical harmonics. So even when you do other, even when you study other subjects like quantum mechanics, especially when you're studying something like hydrogen atom, you would look at it from a spherical polar coordinate view, and there you are trying to do the same thing. You're trying to solve the equation, Schrodinger wave equation, and in the Schrodinger wave equation, again, you will see that you have a del square term in Schrodinger wave equation. That del square term comes from, you have something like del square by 2m, that's representative of momentum p square by 2m. So even in quantum mechanics, you will do a similar separation of variables, and when you do the separation of variables, you will see that the theta and phi part still give you the same spherical harmonics, because when you do time independent picture, you will see that in quantum mechanics that you get the same result of spherical harmonics. So this is a general solution. So in general, our solution would be a combination of this L and M. So what we're going to do is we're going to stop here, and then in the next lecture we'll look at some physical examples and how to solve them using spherical polar coordinates.